equilibrium. We are discussing chemical equilibrium. Now, chemical equilibrium exists in a closed system when the rates of the forward and reverse reactions are equal. Chemical equilibrium is influenced by concentration, temperature, and pressure. So what we're saying is that when a reaction has reached its completion state, so when a reversible reaction has reached a state of completion, its forward and reverse reactions occur at the same rate under the same conditions, but in opposite directions, known as something called a dynamic process. Now, when a system reaches equilibrium, we can do various calculations and we can also disturb this equilibrium. Now, the disturbance in equilibrium can only be by changing concentration, temperature, and pressure. When we disturb this equilibrium, the system has to re-establish equilibrium. In order to re-establish this equilibrium, we need to look at what the system does to re-establish this equilibrium. Remember, when we change the equilibrium, it's like you've got weights on a scale and you change the balance of the scale. So the scale tries to rebalance itself. And the same thing happens in a chemical reaction. It will try to rebalance itself so that it reaches a state of equilibrium again. Now, in order to explain these changes in equilibrium, we use a principle called Le Chatelier's principle. Le Chatelier's principle helps us to explain what happens in a chemical reaction and, more importantly, what happens to the concentrations of reactants and products when we make a change to a system that is already in equilibrium. So when we look at Le Chatelier's principle, we need to look at these rules. Please, we have to make sure we look at all of these and we mention them. So we identify the disturbance. This line you have to write down. Le Chatelier's principle will try to counteract the effect of change and how it counteracts this change. Then which reaction is favored? In other words, which reaction is going to use up or replace the change that we have made? What is the effect of the reactant and the product concentrations? So do the concentrations increase or decrease? And of course, which way equilibrium shifts. Now, we can also look at this in terms of rate. So please remember that as reactants are used up, products are being formed. So we end up with the rate of the forward reaction and the rate of the reverse reaction. Please notice that the forward reaction, the rate decreases because we're using up these, and the rate of the reverse reaction increases because we are producing these. Until we have used up and produced as much as possible, then we reach a state of equilibrium. Equilibrium is where the rate of the forward and reverse reactions are equal. So the best way to look at this is to look at specific examples. The example that I'm going to look at with you today is this N2 plus 3H2 produce 2NH3. This is known as the Haber process, and it is a reversible reaction. So a reversible reaction is usually shown by a forward and a reverse arrow. Now in this reaction, they say this, and they tell you that delta H is minus 92.4 kilojoules per mole. This can also be written as 2NH3 plus 92 kilojoules. When you see energy or heat on the product side, it tells me that heat is given off, so it is exothermic. If you see it on the reactant side, where we say plus heat on the reactant side, it means it is endothermic. And we know that a delta H value that is less than 0 is also an exothermic reaction. So the forward reaction is exothermic, the reverse reaction endothermic. Now the first change I'm going to look at is an increase in concentration. To change the concentration, we add moles of any one of the reactants, and that's how we will change the concentration. Now we can change the concentration of gases and solutions. So in this case, I'm going to add more N2. I'm increasing the concentration of N2. And in future, if you see square brackets, I'm referring to concentration. So what happens when I add N2? It means that one side is heavier than the other. So it now needs to make itself equal again. The only way it can do that is to get rid of this. If I add something, how do I get rid of it? I need to use it up. So Le Chatelier helps us explain this. Using his rules, what was the disturbance? The concentration of N2 is increased. According to Le Chatelier's principle, the system will try to counteract the effect of the disturbance. How does it do it? It will try to reduce the concentration of N2. How is it going to reduce this concentration? By using it up. How can it use it up? The forward reaction needs to work. So the forward reaction is favored because the concentration of N2 and H2 needs to decrease because they're being used up, and we will produce more NH3, so its concentration will increase, and equilibrium shifts in the direction that is being produced where more is being made, so it shifts right, or where in the direction to which things are being used. So here the reactants are being used, they are used to form products. That is why it shifts right. Now we look at a graph. So we initially started with the reaction in equilibrium. That's why we have flat lines. And then what happened? I increased the concentration of N2. This increase here is called a spike. When you see a spike on either one reactant or product, it means that concentration has changed. So concentration, the change in concentration is represented by a sudden spike on the graph. An increase, an upward spike means an increase in concentration, and a downward spike, a decrease in concentration. And then what happened? After it spiked, it was used up, so its concentration decreased. And the concentration of H2 decreased because it was used up even more. And more NH3 was formed, and they all reached equilibrium at a specific point where no more could be produced. So this is the new equilibrium where no more could be produced. Now remember that NH3, we cannot produce more NH3 than the amount of reactant we have. Once H2 is used up, we cannot produce more NH3. Then we get a rate graph. So again, from the rate graph, these are the reactants. The reactants are being used up. They are used up until the reaction stops at first equilibrium. The products are formed until enough product is formed till the end of this first reaction here. Then what happens? What happens is there's this change here because we've added this N2. But once we add it, it needs to be used up again. So its rate will decrease, and this is being formed again, so its rate will increase. The rate will not increase at the same rate as originally because there isn't more of it. It's just using up what I added, and it will re-establish equilibrium. Okay, so if we decrease the concentration of N2, what is the system going to try to do? It is going to try to increase the concentration of N2. So again, according to Le Chatelier, the system will try to counteract the disturbance. It will try to increase the concentration of N2. So which reaction increases the concentration? If I go this way, I use it up. So to make it, I must go backward. That is called the reverse reaction. So the reverse reaction is favored. If the reverse reaction is doing the work, I'm using this, so its concentration will decrease, and I am making these, so its concentration will increase. Which one? Where is the work being done? It is being done from left to right, so from right to left, so equilibrium shifts left. And we can look at the graph again. So we have again, this graph isn't the right graph. I'm just going to draw it for you quickly. So we can look at our graph, and I'm just going to draw it for you quickly. So what happens is we have our axes of concentration against time. And we know that what happened was everything was in equilibrium. And so I had H2, I had NH3, and I had N2. And then I disturbed the equilibrium by decreasing this concentration here. Now when I decrease this concentration here, what did I try to do? I then tried to increase it again. So I'm sure I increased it. I dropped it down, but I increased it. Its increase, however, needs to not be more than what I originally had. What did I do to the NH3? It was in equilibrium, and then I had to use it up. So I used it up, and then remember I've made more of this, so I should have less of this. And what happened to H2? Because I produced more, I already had so much, and then I ended up with more. Now please, I want you to pay attention to that. There's the spike in 1, downward spike, telling me concentration decreased. Okay, what happens to the rate graph? The rate of the forward reaction decreases. Again, let's look at this. Okay, let's draw these together. So the rate of the forward reaction decreases there, and then what happens? When the change happens, that starts to increase because I'm starting to make it. It decreases when I use it up. It increases when I make it. Then what happened here? Its rate was increasing when I was producing it, but now I am using it, and if I am using it, its rate must decrease. Because when the change to equilibrium occurs, what is this telling me? That the reactions have now changed. Different reactions are doing the work. So our rates must show that different reactions are doing the work. And here is a little summary of concentration. So it just says, here's the reaction. The equilibrium responds in such a way as to diminish or decrease the increase or equalize the ratio. Increasing concentration shifts to the right, an increasing concentration of the product shifts the reaction to the left. But it does not affect this equilibrium constant, which we will come back to. Okay, I'm going to stop this video here, and I will upload another video that discusses